Next, let's talk about correlation coefficient and independency. First, some notation. X and Y have the joint PDF. So mu1, mu2 are the means of X and Y. Sigma 1 square and sigma 2 square are the variances of X and Y. So the Ux and Y is a function of X and Y. So these are some common notation. First, let's define the covariance. So variance, we know. Variance of X. So this is just the expected value, X minus mu square. That's the variance. Now here, I define the covariance between X and Y. So it's the expected value, X minus mu1, Y minus mu1, mu2. You can expand its product. So your covariance is this one. Expected value, X and Y, minus the mean product. The expected value of X times the expected value of Y. So this is how we define the covariance. The covariance XX is just the variance of X. Covariance can be anything, any number, not positive, any number. The covariance is between a real line, any number. Now I can do some standardized covariance. So that's the correlation coefficient. The notation is rho. So the numerator is the covariance. The denominator is the product of the standard deviation. So it's the square root of the variance. Now I can do some algebra. So expected value in X and Y is mu1, mu2 plus both sigma 1, sigma 2. So this one is equal to expected value X and Y, X times Y minus mu1, mu2. Sigma 1, sigma 2. So expected value X and Y. This is expected value X, expected value Y. So rho sigma 1, sigma 2 is here. First, let's see how we calculate the correlation coefficient. X and Y have the joint PDF. So X plus Y, the support. X between 0 and 1, Y between 0 and 1. Find the correlation coefficient, rho of X and Y. So we can, for this example, we can get the mean of X, the expected value of X. You can do the double integration directly. We can get the variance of X. So by definition, expected value X squared minus mean square. You can get the sigma 1 square. Since this X and Y are symmetric, so we can mu2 and the sigma 2 square. This is exactly the same as the mean and variance of X. The covariance between X and Y. So by definition, expected value XY minus mean product. So we get the mean. We need to calculate the first term. The first term, expected value, is a double integration. So we can get the covariance. Finally, we can work out the correlation coefficient between X and Y, the rho. The numerator is covariance. Denominator is the square root variance of X, variance of Y. So it's a standard deviation. Don't forget the square root of variance. So we can get the correlation coefficient between X and Y is negative 1/11. Now the next question is how to interpret this rho. What do you mean rho is large or rho is small? What's the meaning of this rho, correlation coefficient? So the correlation coefficient rho proves to be a very useful characteristic of the relationship between X and Y. Now, what kind of relationship? Here is important. Rho is a measure of the intensity of the concentration of the probability for X and Y about a line. So this means this rho characterizes how strong the linear relationship. linear relationship between x and y. Be careful, linear, that's the key. How strong the linear relationship between x and y. Some good properties of this rho. So this rho is always between -1 and 1. So it cannot be 2 or -2. It's always between -1 and 1. For two extreme situations, if rho is 1 or rho equal to -1, so probability y is a plus bx equal to 1. So that means x and y have a perfect linear relationship. Because y is exactly the linear function of x. So they have perfect linear relationship. Now, only difference is the coefficient. B is positive. B is negative. So that's the only difference. Now, if you look at this picture, this is a scatter plot for some data from x and y. So here, that means they have a very strong linear relationship between x and y. So this rho probably is 0.99, for example, very close to 1. This one has a weak positive correlation. So this rho probably, I guess, is about 0.6. This one have a very strong negative correlation. So this rho is 0.9. This one negative, right? So this rho negative 0.6. This one has no correlation. I cannot see any linear pattern. So this rho is probably 0. So this is how we interpret the correlation coefficient. Now, independent. Independent is another type of relationship. Let x1, x2 denote random variables of continuous type. We have the joint, we have the marginal. So for the conditional distribution, right, conditional distribution, by definition, the joint is the conditional times marginal. This is always true by definition of conditional PDF. Now there is a special relationship, like I said. What happened? The conditional PDF of x2 given x1 does not depend on x1. So that means you know x1, you don't know x1, it will not affect the distribution of x2. So if this is true, you can calculate the marginal distribution of x2. You can do some algebra, simple algebra. So later you will see the marginal distribution of x2 is exactly same as the conditional distribution of x2. That also makes sense because the conditional does not depend on x1. I know x1, I don't know x1. It will not affect the distribution of x2. So for this situation, the joint is a product of the margin. The same discussion applies to the discrete case too. So that means x1, x2 have no relationship. You know x1, it does not affect anything. So that's a motivation which can define independency. So x1, x2 are said to be independent if and only if the joint distribution is the same as the product of the marginal distribution. So its joint PDF is equal to the product of the marginal PDF. The joint PMF is the product of the marginal PMF. So this is true for all x1, x2. It's not just for one point. It's for any x1, x2. If this is true, we say x1, x2 are independent. If this is not true, x1, x2 are dependent. Let's take a look at the example. So this is an old example. So this is a joint PDF. You can calculate the marginal PDF. By integrate out x2, you can get a marginal. You can get the marginal PDF of x2 and x1. Now it's very easy to verify. The product is not the same as the joint. So they are not independent. For this example, x and y have the joint PDF for xy. Now the support. Are x and y independent? You can get the marginal for x1. You can get the marginal for x2. Now you can easily verify the joint is same as the product of the marginal. So x and y are independent. That is a useful tool to check independency. Okay, so let x1 and x2 have support. S1, S1 and S2. They have the joint PDF. Then x1 and x2 are independent if and only if fx1, x2, the joint distribution, can be written as a product of these two functions. So you can separate these two functions. So one function is only function of x1. Another function is only function of x2. So you do this kind of separation. This is true. Gxy is greater than 0 when xy is in the support for x1. Hx2 is greater than 0 when x2 is in the support of x2. So there are two things you need to be careful. The first, this guy, you need to do separation. For example, f x1 x2 is x1 plus x2. I don't think you can do separation. Then you can claim x1 x2 are dependent. The second part you need to be careful is this guy, the support. Is the support. Usually, if the support is not the rectangle shape, they must be dependent. So if you want to show independency, the support must be rectangle shape. So we talked about this example before. So they are dependent. This one you can separate. Also look at the support. 0 less than xy less than 1. So the support. This is a rectangle shape. Now we can check this example. The joint PDF is 8xy x2 support 0 less than x1 less than x2 less than 1. The formula 8x1 x2 might suggest to some that x1 and x2 are independent because you can separate x1 and x2. Now look at the support. x1, x2. So x1 less than x2. This is a triangle. The triangle is not a rectangle shape. If we consider the space support, it's not a product space. This should make it clear that in general, x1, x2 must be dependent if the space of positive probability density is bounded by a curve that is neither horizontal or vertical line. So this is not a rectangle shape, so it must be dependent. Now, suppose x1, x2 are independent. We calculate expected value. So expected value of ux1, vx2 is separate. You can separate them. It's expected value ux1, expected value ux2. The conclusion is only true for one direction. So that means what? For example, let's consider the easiest case. If x and xy and x2 are independent, you can get expected value x1 x2 is equal to expected value x1 expected value x2. Now what happened to this direction? If expected value x1 x2 is equal to the product of the expectation, are they independent? So the answer is no. This is not true. This is not true. So here, if these are equal, that basically means covariance of x1, x2 is 0. So that means the rho is 0. So x1, x2, the correlation coefficient is 0. Correlation coefficient is 0 doesn't mean they are independent. Correlation coefficient only characterize the linear relationship. Independency, that means no relationship at all. Whatever relationship, there's no relationship. So this is a stronger result. Independency. This is weaker. So if independent, we can get rho is 0. Rho is 0 doesn't mean they are independent. So there is a counter example. For example, the joint PMF, x and y is 1/3. Support 0, 0, 1, 1, 2, 1. So for this example, you can draw the support. So this is x, this is y. X can be 0, 1, 2. Y can be 0, 1. Now you have mass at 0, 0, 1/3. 1, 1, you have 1/3. 2, 0, 1/3. 0, 0, 0. So this is a joint PMF. So for this problem, definitely they are not independent. You can get the marginal directly. You take the product is not equal to the joint PMF. So x and y are not independent. You can do further calculation. I will leave it as an exercise. You can calculate the rho for this example. Rho is 0. So rho is 0. They are dependent. So this is a counter example for other direction. Rho is 0 doesn't mean they are independent. For the MGF, what's the relationship between independency and MGF? Suppose the joint MGF exists. Now, if they are independent, if and only if the joint MGF is the same as the product of the marginal PMF. For example, let xy be a pair of random variables with a joint PDF. So this is joint PDF. If I look at this support, we know they must be dependent. Now we can verify it using this MGF. I can calculate the MGF for this x and y. So this is expected value e to the t1x plus t2y. Then you do double integration. You can get the MGF. So for this MGF, you let t1 be 0, you will get the MGF for y. You let t2 be 0, you will get the MGF for x. Unfortunately, this is not true. So they are dependent. There are some references.